Hello, this is Fredrik Grek. In this screencast, I will introduce the Bayesian estimators. The Bayesian estimators involve a paradigm shift over the other estimation methods covered in this course. I will be giving references to the likelihood function, so it might be a good idea to check out the related course material beforehand to clearly understand the connections. First, a recap of the Bayes theorem. The Bayes theorem is actually quite old. Andrei Kolmogorov established the axioms of the probability theory in 1933, but Bayes theorem precedes that by 2 centuries. It is an answer to the question, how do we update our belief upon receiving new evidence? What you see on this slide is the Bayes theorem stated through conditional probabilities. The terminology is as follows. The probability of event A is called the a priori. That is based on the distribution we had before evidence. The probability of event A conditional on event B is called the a posteriori. That is our updated belief according to evidence. Of course, the event B is the evidence here. The probability of event B conditional on event A tells us the probability of observing the evidence B given our a priori A holds. This term is also called the likelihood. We will see how Bayes theorem is applied to estimation in the coming slides. It all begins with a fundamental paradigm shift. In other estimation methods covered in this course, the signal model and the parameters controlling that model are interpreted as unknown, but essentially deterministic. The stochastic nature of the data is attributed solely to the additive noise. With Bayesian estimation, we treat these parameters to be estimated as random variables in their own right, with their own distribution and the associated probability density function. So, estimation becomes a matter of updating the probability density function for the parameters and extracting the parameter values out of that probability density function. To appreciate the difference between the classical and Bayesian setting, consider the 2 figures on this slide. On the left-hand side, we have the likelihood function for the DC voltage in Gaussian noise. In that setting, the DC voltage is a deterministic value. We just don't know it. Remember, once we have the data, we end up with the curve marked in red. That corresponds to the likelihood of our data for different values of the controlling parameter theta, which is the DC voltage level in this example. On the right-hand side, we depict the consequence of the paradigm shift. The DC voltage level is also a random variable. In this setting, we talk about the joint probability density function. To understand the operation of the Bayesian estimator, we need to consider the relation between joint probability, the conditional probabilities, and marginal probabilities. On the walls of the 3-dimensional plot, you can see the marginal probability density functions. The denominator of the Bayes theorem is the marginal probability density function for the data. But more importantly, it is the marginal probability density function evaluated for the sampled data. Now, what does that mean? That means we are actually talking about a single point on the marginal probability Px. And that probability is used to normalize the cut through the joint probability to obtain the conditional probability P theta conditioned on x. Now, how does that work? We talk about the conditional probabilities, but how do they look like in this joint probability density function figure on the right-hand side? Intuitively, we may expect the P theta given x to be a curve similar to that on the likelihood function plot. In the end, setting the value of x should correspond to a cut along the value of the joint probability figure. But here's one significant difference. We have to normalize that cut with the corresponding value of the marginal probability density function so that we still have a probability density function whose area under the curve is equal to 1. So, given the sample data xn, we can calculate the probability density function for theta. Even better, we can set up this formulation for the probability density function of x already and use the sample data as the input to this formulation. Now, that is the essence of the Bayesian estimators. But why do we need the conditional probabilities? Don't we have the joint probability? Well, the answer is no. The signal model we adopt gives the conditional probability density function for the data that is conditioned on the controlling parameter theta. Remember, that was the likelihood function when the parameter theta was assumed deterministic but unknown. Here, it is the probability of x conditioned on theta, which is also called the likelihood. As you may observe, we don't have a theta hat yet. That is, we don't have a value for the estimated theta. There are two ways to draw a value from this Bayesian setup. One, you may find the theta value that maximizes the conditional probability density function, p theta conditioned on x, and that is called the maximum a posteriori estimator. Two, you may find the expected value of the conditional probability density function p theta given x. This is called the minimum mean squared estimator. Both estimators are explained in the lecture notes. The solutions to these estimators are very different. Let's see how to combine the problem components to build these estimators. We will consider two methods of extracting parameter values out of the probability density function for parameters. The first method gives the value of the estimate where the probability density function of the a posteriori is maximized, hence the name maximum a posteriori, abbreviated as MAP. The detailed description of the map is given in the lecture notes. Let's see how the map solution is constructed from problem components. We simply begin with the Bayes theorem. The probability density function for theta conditioned on x is written in terms of the probability density function conditioned on theta, that is the likelihood, and the marginal probabilities, probability of theta, probability of x. The Bayesian estimation problem is solved by two components, the likelihood and the a priori. How so? Well, we maximize the a posteriori by taking its derivative with respect to the parameter theta and setting it to 0. And, as you should remember, we can search for the parameter maximizing a function after taking the natural logarithm of that function. The denominator, which is the marginal probability density function px, has no dependence on the parameter theta. The derivative of its logarithm with respect to theta is simply 0. So, we are left with the task of taking the derivatives of the likelihood for the data, that is the PDF of the data conditioned on the parameter theta, and the a priori probability density function for theta. Solving the sum of the partial derivatives for 0 yields the map. The other method gives the expected value for parameters, based on the probability density function of the a posteriori as the parameter estimates. This method corresponds to a minimum mean square error, abbreviated as MMSE estimation, the estimator that minimizes the mean square error for that estimate. You can find the derivation of the MMSE in the lecture notes. We will see now how the expected value formulation is put together from problem components. The idea is straightforward. We have the expression for the expected value of the random parameter theta as seen on the slide. But we are interested in the conditional expected value, which is calculated using the conditional probability density function. The probability density function of the parameter theta conditional on the data x is replaced according to the Bayes theorem. This is a rather tough integral expression. While we can calculate map by just focusing on the likelihood and the a priori, we have to evaluate the whole Bayes theorem expression and then calculate the expected value to achieve the minimum mean square estimator. To compare map with MMSE, consider the Rayleigh distribution for the a posteriori. The expected value for the a posteriori probability density function is as shown in this figure, marked as MMSE. The peak is attained at a different parameter value. But why should we prefer one over the other? First, There's a difference between the criteria. MMSE aims to minimize the mean squared error of the estimation. MAP, on the other hand, aims to keep the estimate within the vicinity of the actual data with greatest probability. It is explained as hit or miss cost function. If the estimate is off by a certain amount, we get no reward. If the estimate is close enough, we get all the reward. The other difference concerns the implementation. MAP is easier to implement, while MMSE requires solving some complicated integrals. Third difference, MMSE can readily handle parameter vectors, but MAP is formulated for scalar parameters. Extension to vector form requires solving those integrals found in the MMSE. So you need to choose which method to use depending on the problem at hand. This slide concludes the screencast. If you have any questions, please contact us. Have a nice day.